Hi guys, so that's going to be the last problem I'm going to go over, so the last video. And here is another problem with a few questions for you. They talk about an experiment that was done with a diverging lens and a converging lens, and they are 10 centimeters away from each other. And here you have the object. The object can be placed here, or they can be placed in between the lenses. The focal length for the diverging lens and the converging lens is 10 centimeter. Okay, so this one has a focal length of 10 centimeter. This one has a focal length of 10 centimeter. And the result here for the experiment is here. So P1 will be the distance of the object. So the distance between the object and lens 1. Q1 will be the distance between the image, the first image, because of lens 1. So you see it's negative, so it means it's going to be placed here. And then you have the P2, it's going to be the place of the object relative to that converging lens. You see it's just 10 plus 6.67, so it's positive. So it means that the object will be placed at 16.67 from that lens, and that will be the distance from that lens of the final image, and that will be the final magnitude. So M is going to be equals to M1 times M2. Okay, so you have all the experiments here. So what they show you here, you have a negative number here. That means that the object is placed on that side of the lens. You could do that. Here, we already talked about it, but here is an example of the setup. You have a diverging lens and you have a converging lens. So first you have a virtual image because of the diverging lens. It's going to be virtual, it's going to be smaller, and it's going to be upright. That image here becomes an object for the converging lens. Okay, even though it's virtual, it becomes like an object, a real object for the converging lens. And the final image will be here. It's going to be upside down and real. And then you can move the object. You can make it go closer, and even you can bring it in between the lenses, and everything is reported here in that table. So it looks complicated, but actually the questions are not, they give you all those numbers and there is very little computations in the question. So first question, it says, as the object moves toward the converging lens, so they are not talking about that setup, and crosses the focal point, what happened to his image? So this is a very easy question. It's just telling you that if you have a converging lens, this one, what's going to happen if the object, converging lens, yeah, what's happening if the object is inside the focal distance? You see what happened is that you get a virtual image which is enlarged and upright, so it becomes like a magnifying glass. So which answer is that? So it was real, and no, but it was before entering in that zone. So before entering in that zone, you see it was real upside down, and now it's virtual and upright. So it's not A, from real and inverted to real and upright. No, the image goes from being real, upright to virtual, inverted. No, the image goes from being real, inverted to virtual and upright. Yes, so Answer is D. D. So let's keep the table. Okay, number 44. In moving the object from the position C to the position D, trial C, trial D, what happens to the final image? So it's the wording can be confusing. Okay, from C to D. So they want you to compare C to D. So C, you see that the final object, the magnitude is -2. So it was enlarged by a factor of 2, but it's upside down. In this experiment, you get an image which is also enlarged, but is upright. But the confusion is you go from here to there. So what's happening from here to there is that the image from here to there, here it's going to be bigger, but it's inverted, right? So because here it was upside down, this one is upright. So going from C to D, you will get a bigger image, but the image will be inverted relative to the image in C. So the wording is, have to be careful with the wording. So it becomes larger and inverts when you compare C to D. Okay? Yes. Okay. Which trial the final image form on lens 1? So it means the final image, you want that final image to be here. The final image wants to be here. So relative to lens 2, that means that relative to lens 2, you want the image to be at -10 relative to lens 2. Okay? So if relative to lens 2 in this domain here, it's negative. In that domain here, the distance is positive. So relative to lens 2, that position here equals to -10. So that will be trial D. Let's see if we have trial D. So D. D. Okay, here is an easy one. What's the magnification of lens 2 trial B? So they give you points for free, because this one is very easy. So B. So what's the definition for magnification? Magnification is, magnification by definition is minus the distance over 2, which is minus, and I'm lost. So it's going to be minus. I forgot what was the question? E? Was it E? B. B. So B, so it's minus, so Q2 over P2. So it's going to be minus 30 over 15. So that's going to be -2. So the answer is A. The answer is A, I think. Okay, here is another easy question for a converging lens, so nothing to do with the setup. when the image formed at infinity. So by definition, when the image is formed at infinity, that means the object is at the focal length, right? So if you put the object here, you see the image is very far away at infinity. It's not really infinity, it's very far relative to that distance here. So anyway, the answer will be when the object is at one focal point. So that's an easy question. So if you place the object, okay, again, it's not nothing to do with the setup. So diverging length, so they're telling you that now if you have a diverging length, what's happening if you place that object on the other side? It doesn't really matter, right? So if you put the object here, you still get a virtual image on that side. The virtual image will be virtual, obviously, and it will be smaller and it will be upright. So it doesn't matter if you place the image here or if you place it there. Nature cannot tell apart that side or this side. From the point of view of the lens, it doesn't matter if the object is here or there. Okay, so I think it's an easy question. You still get a virtual upright. Virtual upright, yes. Okay, let's see number 49. So these questions have nothing to do with the setup. So really, they put all those numbers just to scare you and confuse you, and you're going to lose your time, looking at those numbers, trying to make sense of them. Don't do that, right? You just read the text and go straight to the questions, because, there was no point to have all those numbers except for confusing exam takers. So if an object is placed in front of a concave mirror, so concave mirror is a converging mirror, inside its focal length, the image can be best described as, so it's going to be like a magnifying glass, right? It's going to be virtual and upright, okay? So let's see. If you have a mirror here, it's a convex mirror. So here the image is upside down and it's real. You can display it on the screen. If it's at that distance here, we discussed that before. So that distance here is twice the focal length. That distance here is the radius of the mirror. So you get an image which is real and upside down and the same size. If you move it here, you get something smaller. If you make it go closer to the focal point, you get something larger. So it's enlarged, upside down, and real. And if it's inside here, what you get something which is upright, inverted, not inverted, upright, virtual, upright, virtual, and enlarged. And the image is beyond the mirror, right? You get a virtual image. So the answer is virtual and upright. Okay, so this one is kind of tricky questions, and you need to know about polarization of light. So light is an electromagnetic wave, okay? And so it's a transverse wave. So it means if the light is moving a straight line, when the light obviously is moving along a straight line, the electric field is going to go up and down and up and down and up and down, right? So that's going to be the electric field moving perpendicular to the direction of propagation. But if it's unpolarized, that means light coming from a real object, coming from the sky, coming from, I don't know, a tree, light will be unpolarized. So it means that the electric field is going to go up and down, up and down, up and down in this direction, also in that direction, or also in this direction, also in that direction, right? So you can do research about this. You will see that light will be a transverse wave, right? So the electric field is shaking in a direction perpendicular to the direction of propagation of the disturbance. Now, when it's reflected off, for example, a road, when you are driving and you have light, that will be reflected off a medium, it gets polarized. So now the electric field can only shake in this direction, and the light that is refracted is also polarized. Okay, so that means the intensity of light will be smaller here when it's refracted and smaller here when it's polarized. That's why we wear Polaroid when we are driving, so it will stop the light that is reflected from the road. So we are not blind. Okay, so that's called polarization. And you can go online, you can buy those filters called polarizing filter. You take those little slides here. For example, the light coming from your computer is polarized, so it's shaking only in one direction. You take those slides here, you rotate them, and all of a sudden your screen becomes dark. You see, if you put them here perpendicular to each other, it's going to be all dark. Okay, so this is called polarization of light. So they talk here in this question, they talk about a mirage. So this is an example of a mirage here. So you see, light is refracted because the layers of the atmosphere have different temperature. So light will be refracted and you're going to see a virtual image there. Okay, but that image, the light coming from that image will be polarized. So it's going to go only in one direction. So if you look at that light with a Polaroid, like sunglasses that are polarized, it's going to decrease the intensity of light. You're not even going to see the virtual image, right? So that was not an easy question. So the answer is you have to look for a polarizer. So this question is exactly the same. So the answer is B. B. So not only you can if you so polarizer, so these are like sunglasses. So that means they not only they are polarizing light, okay, but that means they only let light with an electric field that goes, for example, vertically up and down, and it's killing all the other electric fields. So it only lets light going through, only if the electric field is going, for example, vertically. Not only that, but it's also decrease the intensity of light. That's what it says here. So 50% we really don't care. Explain that when the polarizer was used to filter ambient light that had been reflected on a plastic surface, the amount of light transmitted varied with polarizer alignment, but it just means that the plastic is acting itself as semi-polarizer. So that means the light that will be reflecting from the plastic get polarized. So 51, the answer is C. Now, if I can have a better picture polarization of light. Let's see. So you see that here you force the electric field to go linearly, so up and down. Looking for a better picture. So you see here you have light coming from a real object. It goes for a polarizer like the slide, and now light can only, the electric field can only shake up and down and up and down and up and down, and all the other ones have been cancelled. You can see that here. You see you have the electric field here. You have one wave with electric field shaking in this direction. Here it's shaking in that direction, that direction. It goes through that polarizer, and now it's only shaking in this direction, which means that the intensity of light will decrease as well. Now you have another polarizer in the opposite direction, like here. So there it will be all dark. So polarization of light is very interesting. And so you see you have those sunglasses here that would let light coming from an object on the road, but the light that will be reflected from the road or reflected from the highway will be stopped, right? Because it's polarizing light in this direction. So not only it's polarizing, but it decreases the intensity as well. Okay, so I'm sure you can do some research on that. So the answer was C. So this question here, you can pause the video, but we already discussed that if you have, when you consider refraction, here, you're going to have less refraction if instead of going from air to glass, for example, you go from water to glass, right? So because there is not enough contrast, so you have less refraction. So if we are talking about a lens like this one, talking about a converging lens, right? So what does it mean that the lens is less refractive? So when the lens is less refractive, you see you decrease the index of refraction. The effect, the result will be you increase the focal distance. If a lens is more refractive, then you decrease the focal distance, right? Sorry, so in the MCAT, you have this question I saw come back. Okay, so it's the idea of contrast. If you increase the contrast, so now if it's air here and very thick glass, you see you're gonna have more refraction. If you have more contrast here, you have less refraction. So conclusion, the answer is increase in the focal length of the eye, so A. So yeah, in the water, it's harder to focus. Okay, that's it, and that no more problems here.